Hello everybody. Welcome to yet another awesome tutorial. My name is Urban Bradesko here with Rebelway, and today we're going to be taking a look at how to create this massive Star Destroyer coming through ice. I do have to say I tend to overdo depth of field. I feel like I'm like J.J. Abrams with depth of field. What J.J. does with lens flares, I tend to do with depth of field, but I just can't help it. When you have unlimited power and you can create unlimited anamorphic bokeh, I just cannot help myself. So in this tutorial, we're going to be taking a look at how to create the ice simulations, the snow simulations, the wind, and the RBD destruction. And then we're going to be going into Solaris to see how everything is rendered and assembled. So here's the Solaris context. You can see how it looks like. It's pretty fast, almost pretty much in real time, scrubbing through this, playing around in the scene. If I do a quick render, I believe it took between 8 to 15 minutes per frame with just the ship and the ice. And then I was rendering the snow separately, but it's pretty fast, quite responsive. So you have to do a few tricks to get it to work properly on this scale. But before we jump into this, before we go through this setup, which is the main setup, and I'll clean it up a bit more than this, and we're gonna be providing you guys this setup so you can play around yourself. I will be just doing an overview, like an extensive overview of this one, because there's so many different setups that I would rather you guys go through them at your own pace and really learn. I feel like that's the best way to learn, if you really dig into this yourself. And this is this snow setups, but I will go through everything so you know how everything works and where to find the setups. But first we're gonna go through how to do the same setup, but in a very simplified version of what we were doing with the Star Destroyer. So let's get to it. All right, so we are in the simplified version of the scene. This is what we're going to be doing. Let's see if I do a few frames of simulation. You can see we're going to be fracturing this simple example like here. And the way to do this, let's do it. I will just borrow this part. So I'm doing a simple Voronoi fracture here. If you wish, you can use the material fracture. If I do a quick box here, you can, like I said, use the Voronoi because it was working fine enough. You can see in some cases you can see the Voronoi shapes, but because we were using a bit more complex or more interesting, I guess, constraints, that was not such a big problem for this in this case. So we are doing the RBD material fracture, and it's doing the Voronoi fracture pattern here, but if you use details, it's gonna break that up and it's gonna give you nice shapes. It's using a Boolean inside. It's got a big network here, so it's difficult to control if you want to change anything. So I tend to just do it manually myself. You can also use a glass pattern. And I actually encourage you guys to try this and use this material fracture instead of the Voronoi, just to see if you get different results. Alrighty. So what this will give us is out of the Voronoi, you get the geometry and you get the constraints. Now, this won't work out of the gate. You have to do a bit of finessing first, and I will just borrow this DOP network here, just so I don't have to reconstruct one. It's a very simple DOP network, and you can start using the RBD solver as well. And in some cases, this will actually be more beneficial because you have this emit RBD that we're going to have to trick the system later to constantly emit small RBD. You have your breaking thresholds here that we're going to have to set manually, this distance one or the impact threshold. You have a lot of this here, but again, because it's so it's pre-built, sometimes I have a hard time controlling it because it does everything, but then if I want to change something, it's so super difficult. So I tend to just do it manually here. So here, forget about this for a second. We have a basic setup, basic RBD setup, and just remember, yeah, no, it should be fine. So we have our ground here. This should be invisible. Oh, we have to plug some things in. So we have our ground here, and for this to work, because we're using the RBD solver, we have to pack this. So pack it. We don't need to create names, but we do want to pack it. So if we plug this in now, we should see at least something happening, which is, you know, we at least get our geometry here. Now we do need to so this is our ground. We do need to bring in our ship, and our ship in this case was just this test rubber toy. So if I bring this here, it's a toy, I assemble it, and then I transform it here. I just move the position. I don't know where it was. Here, and then I move it to our fracturing. I think it's a bit big. Put it back to 20, maybe 30. Yeah, 30 sounds good. And it has an animation going up. I also add a few attributes like activated and animated. Plug this in the second stream, and we should start seeing some collision happening. If I go a bit further, for some reason it doesn't appear. So we have this. Let's see what's happening. Our ship is second context geometry, use object transforms. So go forward. Oh, it's just a bit too low. It's animated, so it starts a bit higher. And let's see the magic happen. Oh, also, I will change this to 1000. It's going to be a lot faster. It's going to make a huge difference. Here we go. Yay. So this is the basic fracturing setup that I was using for everything here, really. If we take a look at how this looks, it's going to be more detailed, 100%. This is just kind of the middle part, but it's the same logic that we're going to be doing. It's literally the same. I just want to explain it on a simplified version first before we dive into that one. So this is what we have. We don't have any constraints happening yet. And if we go outside, this is where we get the constraints from. And in this case, nothing is working yet because we need to apply some attributes to our constraints. So the system knows what it's actually. You have to create a few attributes for the RBD to know what to use them for. So let's create a RBD constraints properties. And these are the constraints. So we only need them to work on this pinkish line. So yeah, those are the constraints. And if we create another null coming out, you will see we now have the constraint name, propagation, strength, all of that the solver actually needs. And right out of the gate, we get our glue constraint name. That's the basic one. And we can also then later say switch constraint. You can see here, switch constraint type when broken, and you enable this and it's going to switch it to soft. Let's keep it active like that and plug this in the last context. And now we do need to plug in our constraint network and our constraints here. And we have our glue constraints here that are corresponding to the name glue. And we have our soft constraints here corresponding to the name soft. So if I do this, you can see everything kind of breaks from the beginning and we are just left with the blue soft constraints, and they're just gonna stretch like that forever, which also creates like a cool webbing effect. If you think about it, it's actually pretty cool, but that's not exactly what we want. If we go back a bit, and here, if we change the strength to maybe something like 18K 500, I think that was the default strength. They still all break. Here now they don't break immediately, and you can see when the red constraints start breaking, we get the blue ones appearing. So we start getting this. And also now it might be cool if we change the stiffness to 10. You will see everything is going to become, well, and let's change the strength back. And our rubber toy is going to get like a hoodie, like a hat thing happening. So this is what the soft constraint is doing. It's kind of slowly, you can see you get a very cool looking, almost like cloth looking appearance. So we want some of that, but mostly we want the ice. And the ice cracking you get with, we're gonna get that with the glue constraints. All right, so this is essentially what we recreated here. And here we did a few other things. So we have our constraints, and I put down a glue cluster. What this will do is it's going to give us a few attributes. Go a bit higher. It's going to give us a few attributes that we can use to control our clusters. And one of the attributes is called with this internal strength. By default, it's set to -1. So I can immediately show you how that looks like. If we say strength equals -1, you will see we get these inter clusters. So let's call them the intra constraints, and then you have the outra constraints like this. You can see that this looks pretty cool, and this will create the clusters for us. If we can visualize them here, you can change the scale of them so they're a bit bigger. And based on this, you can now start controlling where you want your fractures to be. With this, you can now say, if your strength is this, then you're a bit stronger in the inside and weaker on the outside. But let's, like a funny thing that happens here is this glue cluster will actually destroy our strength attribute. So you see here, it was 1800, where this will now set it to -1 or 1. That's how we were creating this group. Like we were just grabbing everything that's -1. But what we actually want is this to be the same. So we don't want it to overwrite. Say copy parameter, paste reference. So now it's 18. Now this will stop working, but we can say is higher than 10, let's say. And now this will create those groups again. Because you will see it's still going to create that attribute, but now it's going to be 1801, or you can just say equals to 1, and this will work as well. All right, so this is essentially what I'm doing here in this wrangle. Visualize. What I'm saying here is everything that was in that inside group become red. So if the strength equals to 1, you are red. Also, you don't have a constraint name, which means that everything that is red is immediately going to get removed. The same thing for the next constraint name. The next constraint name attribute comes from this fella. When we set it to switch constraints, we say enable, we get the next constraint name. And again, the RBD will know that when our constraint name is broken, switch it to the next constraint name. But what I'm saying here is when you do switch it to the next constraint name, everything that's yellow doesn't get a constraint name. So immediately remove it. Maybe this is a bit counterintuitive, but it does make sense that it creates more interesting clusters. So the way we are doing that is with the rest length. And again, the rest length we get from the constraints. If I do a quick color here, and you can see how a simple setup, like we started with a very simple setup, and already we are getting a bit more advanced with attribute. So this is on primitives. And what was it called? The rest length. I can do this. Yes, rest length. And let's start bumping it up. You can see the rest length is going to give us, it's going to measure the length between the constraints. And based on this, you can also create a more interesting map. And that's what I'm doing here with the yellow ones. And if we bump this up to 4K now, maybe 4K, you will see the map that we're creating. All right. All right. So we have this now, and we can now plug this into our constraints, plug that back in. So now immediately in the beginning, you can see we don't have everything that's in between in that red group before, that was in that red group, is now removed. And this will give us interesting fractures from the beginning, as you can see here. This is kind of the icy look that we're getting now. And so there are two ways of going around this. You can either create clusters, or not clusters, but fractures here with the material fracture, right? And create more details coming from this. Or you can fracture it a lot with the with the Voronoi fracture, and that will, oh, my touch was on, it's doing some weird things. With the Voronoi fracture, we fracture a lot of it, and now we are controlling it with our constraints. So just a different way of working around it. So you can see now we're actually getting something cool. Why are we not seeing the constraints? What happened? I think I have a viewport bug again. So let me restart it. Here we go. I don't know what happened. But yeah, now you can see, so everything that's breaking here, you can see everything that broke became a blue soft constraint. And that's pretty cool. That's kind of the fractures we're getting now. I think our glue is maybe a bit too strong. So let's go with 10. Now it's gonna break more easily, and you can see we immediately got more of those blue spots. Just waiting for our toy to arrive. But this will still give us nice fractures, but now they're going to be a bit more floppy, and that's kind of that's also not bad. Also, let's release the stiffness here to 1. So you can see how we are controlling our fracturing now with the constraints. There is one more element to this, and I'm going to show it in a second. The problem is our glue is actually breaking, but our soft constraints are not breaking. We don't have a threshold for them yet. So they will just always stay like this. Even if they become active from the glue, they will stay like this. And that's not the best way. I mean, it looks cool, right? It's very fun. Like how he's like, yep, hello, hello. But we need to break them with a threshold. And if you remember before on the RBD solver, we had that. And we can do this in a SOP solver. You connect it here to the constraint solvers. And this last piece is our constraints. And we can say everything that's on the soft, you can go here. You say soft, right? Not next, but the current. So name, say soft. So everything that's on the soft constraint. If the distance is bigger than 3, which is an attribute here, you can see there's a distance attribute that will get bigger. So if we stay here and go here and sim this, see this distance attribute gets calculated. And based on this distance, you can say if it's bigger than 3, which right now nothing is bigger than 3, or maybe like 1 is. But if you are bigger than 3, you get you snap essentially. So let's see if that works. So now we should see a few of them snapping after they get hit by our toy. Let's put a threshold to something smaller just to see if this is working. Yeah, okay, so it was working, but the threshold was not being activated, so 1.5. It all depends. You need to finesse this every time, to be honest. Maybe 2. Based on your, it's based on your scene, how big your pieces are, how big is that, how big is this. So every time you change it, it's going to be different. So you can see now a few of them snapped already, and now you don't get those big flaps anymore. These are still not snapping because their distance is too close. They haven't reached that threshold yet. So yeah, that's how you set another layer of braking. So that's pretty much that ice. It's literally this. I haven't done anything else to it. All right, so that's our basic setup for the RBD. All right, so let's continue with the uppress system. So this is essentially where we left off. We have the same thing here. I will continue on this side just because it's a bit easier and I was getting some nice breakups and it's pretty much the same setup. And I will actually increase the glue constraint so I get a bit more bigger fractures happening. It's going to be easier to illustrate the uppress system like that. Yeah, that's fine. All right, so for the upressing, we time shift our geometry and we have to store our original name. It's very important because this transform pieces is working on the name, and what our main goal is to get the exact same transform. You can see it's exactly the same, but with more pieces in between. So this guy has 40,000 pieces, and here we have 4,000 pieces. We are essentially fracturing each piece again quite a few times, and that will create, see that, and we just refracture it inside per piece. So we need to, the reason why we need to store our original name is because the Voronoi is going to change it again. So if we just store it just so it's safe and secure, and the Voronoi can do whatever it wants, and we will still retain our name. So we're doing, we unpack our geometry here per each piece. And then we do a scatter and another Voronoi fracture, and it takes some time. That's why I have it in a compile block, so it's quite a lot faster when it's multi-threaded. Oh no, it's thinking again. Yeah, sometimes it does this and then the compile as well. Don't know exactly why, but it's a bit tedious. Yeah, like so. Does it twice. Anyway, so now we assemble this again, and we just transform our original name, and this will all move together. Keep in mind, you have to do this on your points. So we have the points, store the original name, and now we transfer it. And everything's going to work like magic. Like I'm saying, the name attribute is really kind of the main driving force here. If anything is wrong, it's because your name is your name is wrong. The next step is, if you remember those intra groups that we were creating here, we can blast them, scatter points on top of them, and color them white, and color everything else black. Turn this on just for visualization purposes. So this is black, this is white. Transfer the color. All right, transfer the color, and this will be our activation group. Everything that is white is going to be active. We can add a bit of noise just to add a bit more variance to our activation. But for now, I will leave it at the linear one, just so because it's easier to see. All right, so we do that. We turn off this, and now everything is still on our geometry. I bring in our points here again because I didn't want to drag everything up to here. You can see I do the name thing again. And now keep in mind, this is propagating. This is propagating through our points, like so. I put down a color just because it's not okay to store attributes in points. That's why I create an activate me group here. Well, activate me point attribute that is somewhere here. Activate me. You see it's 1, and everything that's not activated is 0. So we transform our pieces again, like so, like we were doing here. This was just to illustrate here, and I put activate me is 1 in a group, so you can see where it's working now. Everything that's green is going to get activated, and you can see how that is propagating. Cool. So now we say this geometry, we actually want everything to be inactive. We just want it to be animated. This is what this is saying. Active is 0, animated is 1. This is something that is internally known in the RBD. It will know. If we don't say it that it's animated, nothing will be moving. If it's animated, then it's going to be using the transform and actually move the pieces. And then in this guy, we're saying, just work on the active G group, which is this group, and just put it after the first frame, put it so it's active, and then animated becomes 0. So this group is going to be propagating, and it's going to just become active each time it enters this group. This will become active. And after we do this, also keep in mind, you need to, on the ground now, you need to say override attributes active and animated. So it will check these attributes each frame. So because remember our active attribute is actually changing from frame to frame because it's propagating. So because it's propagating, you have to say each frame check what value you are. And if you became active, you are now active, right? And if you were on the previous frame, if you were animated, you're no longer animated. And you will see now slowly our pieces are going to become active on kind of on the sides. You can see everything that's breaking, kind of eroding inside. These are our custom activation pieces. Now keep in mind, this is a very simple way of activating. You can activate it activate them in any way you want. And Saber actually in our Mastering Destruction workshop goes much more into this forensic details about how to activate it in a smart way based on distance and all of that. So if you really want to get into that and create even more interesting, better fractures, definitely check that out if you want to learn more about destruction. But you can see this is now, so the big pieces are still animated and the small pieces are starting to get reactivated and reintroduced in the simulation. So that's pretty cool. All right, so if I do a quick recap, that's our activation, that's it, that's the activation system. And you can see if we view this and if we view this, you can see this, the main base skeleton of the sim is still the same, but we were just adding detail on top. You can see this piece is exactly the same. The simulation is exactly the same, except we are adding and simming additional elements on top. So that's your uprest system. And this is the base of everything I was doing later in the main project. This is the core. And yeah, let's take a look at how, let's jump into the juicy parts here and kind of go through the setup as well. All right. We are here, everybody. This is it. This is the main event. All right, so it's gonna take some time to get through this. Trust me, I might make a few mistakes along the way as well, because it's a big setup. Let's start at the beginning. Before we get to this, we have a big ship. It's a big ship, and because it's so big, we have to do a few setups to make this more optimized. Otherwise, this is not gonna fly. I think like 80% of any RBD setup is actually like just cleaning stuff up and making it ready for destruction. And then the 20% is breaking it, creating constraints and simming it. So we have a big ship here. There's nothing special. Like I said, you guys are going to get the hip file so you can dig and dive through this yourself. But here we are just doing some transforms, scaling it up and animating. That's it. We go here. I do a few clippings, and this is again this optimization that I was talking about. So I clip the top, I split the antenna thingies, and we split. It's saving. Takes a while to save. We split the antennas and so on and so forth. To optimize this, we need to create a proxy geometry. And to create a proxy geometry, we're going to do a fun thing with min distance. Sorry, min pause, not min distance, min pause. So what we do is we take the box, we do a mat size, so it's the same size as this. We divide it just to get more polygons, and then we throw it in the min pause. And so the min pause is just doing, it's going to take the position from the second input, and it's going to say, what is the closest position? And that from the surface, and just take that position, and now I have that position. So our points kind of just get squished into the closest positions that they can. And that gives us something, but it's not usable yet. And let me show you guys what I mean here. If I throw this out. So we get this, we convert it into VDB, convert it back to polygons, and then I do a push with normals. This is not super important, but sometimes if things get stuck a bit, it can help, and you'll see what I mean. Because once you do this once, this is your new geometry. Well, we can redo the whole setup we can say now take this and find your closest points, and it's going to find different points now because the geometry itself is closer to the points. So if you just redo this, now if you just do it again, you will see it's going to be even closer. So this was the first one, this is the second one. If you redo this again, we are going to get closer. We're almost perfect now. We're getting very close to our geometry. You know, we are retaining the silhouette. So we have to do this a few times, but what if you just put this into a for loop and do it by count? And we just do it 5 times. Essentially just repeats this process 5 times, gets the feedback and redo it again. And that's how we get our proxy geometry. So that's pretty cool, right? So we have to do this on every geometry. Inside here, it's the same setup. And we just blast through it. This one, I feel like that's the whole ship. So it takes a bit longer to do. Still super fast though. For what it's doing, it's quite fast. All right, almost there. Here we go. And you have a very good proxy geometry. Imagine this has so many small elements, and also it's hollow inside and a lot of things are not connected. So maybe your first thinking would be, oh, maybe I need to fill up the holes and then convert it into a VDB. But if you try to do that, you're gonna enter a world of pain. Let me tell you that. All right. So once we do that, we need to split it into 2 groups. So this is the top group and the bottom group. It's just going to make it a lot easier. And then we do a convex decomposition. I'll only do it on the left side because the whole ship takes quite some time to do. And this essentially creates convex pieces that we're going to use in our simulation. This is convex is something that Bullet prefers. And it's going to make it a lot easier for us to sim on this geometry versus simming. Well, if you try to do concave pieces, it's going to be very glitchy. It's not going to work well, and it's going to be uber slow. So this helps a lot with our collision. So what we need now is to do it on the other side, and that's how it looks like. You can see the whole ship gets pieces inside as well. So it's super sturdy, and once we animate it, super fast. Here I was doing some deleting the small parts, but for this to work, you need to unpack it. So this is not really working like it should. And then I was assembling it, even though it's already assembled. So, but I was creating the name attribute, but didn't pack it again. So, okay, so yeah, this was just for the name attribute. And then I cache it again, and then I pack it again. So I'm not sure why I was doing that, but I guess I pack it again based on the pack it. So, okay, so this, I was unpacking it here. Was I packing it here? Yeah, see, that's what I'm saying. There's a few loopholes in this setup that I need to clean up, but don't worry about this. This is essentially, so you pack it, you create the name attribute, that's it. And now we transform it, and you can see it's super fast based on how many pieces and how everything, like what we actually did with the geometry. So, and then we do the active and animated here as well, just in case. And you can see, yeah, that's the bulk of the optimization here. Quite important. If we continue now, with the setup, we have to do a ground geometry. It looks like this. And it's just a plane with a bunch of RBD. It's the same thing to what we were doing before on the simple example. The only difference is I'm doing it in a bit more complex way, and it's nothing scary. It's still super easy. But it just makes it a bit more diverse. And I'll show you how in a second once it computes. Okay, so what we're doing here is we're doing an initial Voronoi fracture. Don't worry about these guys. They're not really doing anything, as you can see. but in theory they are adding some detail to the pieces, but almost invisible. What I'm doing here is I'm doing a split between this and this. So this geometry and these pieces, they will have, actually, I think we're supposed to do it like this. Let's see, where are you? You are here. Okay, so you have this geometry and this geometry. So everything inside of here, and you can just select them, you know, select the range. Maybe we can do even 2000, doesn't really matter. Maybe more of them, maybe 3000. So these pieces are gonna get more fractures, so 50 versus 5. So everything that comes here is gonna be super fractured. And then on the other side, they will still be oppressed, fractured, but not as much. And this will just create more variety in the sim. Just let it cache there for a second. There you go, more fractures. And that's pretty much what I'm doing on the left side, but I was caching. So this is the side that I chose, and this is the same, it just has more variation. All right, continue. Test bounds, super important for a quick sim. I don't want to sim and test on the whole thing. It's super slow, trust me, it takes like an hour and a half. We want to sim on a small patch. This is for optimization purposes, and this is just for testing. When you do the final sim, you remove this. We unpack it. We do connect adjacent pieces. It's and we do. Let me first see how it looks. You can see we get to a very similar place. Actually, it's the same thing, and we have the same attributes here, but we're doing it in a more in a different way. It just takes a bit more understanding of attributes in Houdini. So let me break it down for you. We do connect adjacent pieces. It's the same, pretty much the same thing that our, what was it, Voronoi fracture is doing with the constraints here. Because we're not doing a Voronoi fracture here, we don't have any constraints, so we just build them from points. That's why we have to unpack this, because we are doing from surface points. So we get this cool web of constraints, so that's cool. And then this part is essentially just doing two Voronoi noises, adding them together and pushing them into seed. Now, how does that look like? It looks like this. And you can see this is very similar to what we were getting with the glue cluster. Actually, if we plug the glue cluster in, you can see this is also creating that Voronoi pattern. The only functionality that we have here is that we can create two noises and create more complex patterns by combining different noises, but it's pretty much the same thing. All right, so we have our seed attribute now. We push it through the RBD constraint. Let me just remove the color. RBD properties, same thing, glue. This was still using the old RBD properties. Same thing, in this case, you just put this to enable. Just if anybody's confused, this had it here. I almost feel like this was easier to see, but it's pretty much the same. We have a null here, nothing special. This is to visualize the rest length that I was showing you guys in the previous example. But this is how the rest length looks like here. And then we have the constraint building. So you can see we are getting the same visualization that we were getting before here. It's the same thing, but here we were using the glue cluster, and here we are doing it in a different way, but it's the same thing, honestly. So what we're doing here is essentially comparing. We are looking for that. Actually, let me bring the color back. We're gonna need it. We're looking for attributes for this seed attribute that we are exporting. And we want to see what attributes have that. So here, there's a pass in between. So these points, these ones have the seed, and some of them, I don't know if it's the other way around in this case. Maybe these guys don't and these have them. But you can see there's a transition between these attributes here. And based on these transitions, we can kind of check. We can do a check. If seed is not equal to seed2, then you're in between or you are inside, right? And the way we are doing that is if we take a look at this code here for a second. So what this code is saying, we're doing a prim point and we need to get 2 points. We need to get this point and this point. And this point will tell us then we can grab the seed attribute from this point and this point. And if it's not the same, if this point and this point has a different seed attribute, then just remove or reveal the constraint. So prim point converts a primitive / vertex pair into a point number. So what does that mean? See, we're writing this into 0.1 and 0.2. So each prim has 2 vertex points on each side. And we just want to know what point are they connected to. What point is this vertex connected to? And what point is this vertex connected to? And each primitive has 2 vertex points. See, 0 and 1. The way we know this is if we go here and remove this, and remove the inverse and go into the primitives, into the vertex, we can see we are running. Right now, this is primitive 0 because it's the first one. But here you can see this is the primitive number. The first number here, 0. 0, 0 means primitive 0, vertex 0. Here, it means primitive 0, vertex 1. And then here we have the point number associated with that vertex number. All right. So that's how we know what attribute to pick. So once we get our points, once we know like what is this point and what is that point, we can say, tell me what is the seed attribute on this point and this point. So 0.1, 0.2. And now we can compare. And we can say if seed is not the same as seed2, let's say here in between, let's remove this color here. So it's actually here. See, this is the line where they're not the same. Color that red. If you're not the same, color it red. That's what we're looking at. And we were doing the same thing with the glue cluster before. We're doing a few more things here. We're saving again. We're doing a few more things here with the else if, and we're basing it on the rest length like we did before. And this is everything that is rest length less than 1.4 is yellow. All right, so I think everything else is clear. The only thing that we're doing different in this case is we are pushing everything and creating a point out of it. So essentially, we are creating unique points and literally going, because before the points were connecting between the centroids, as you can see here. This is the centroid of this piece, and this is the centroid of that piece. But what we're doing now is when we put them to 0, we are literally living in between those pieces. Like so. We are literally in between the pieces, and that's where the constraints are going to work the best, especially the soft constraint is the most efficient in that way. And that actually changes the dynamics of the simulation in a lot of ways, especially because we are breaking them based on that distance attribute. And the distance attribute is going to change based on how far apart our pieces are, or actually how far apart our constraints are. So keep that in mind as well. For now, I'm going to turn them off because otherwise it's going to be difficult to see the constraints in the .NET. So if we go inside, same setup as before. Oh, and we crashed. All right, let me restart real fast. All right, we're back. Let me make more space here. More space. Where are we? Oh, at the beginning. We're still here. All right. Let's go inside. This is the same setup as we had before in the simple example. Let me see the constraints. Here we go. So the ones that are breaking are turning blue, and now we can actually see them. And let's do a sim, and I will show you the difference between if you then scale your points, actually your constraints to 0. So it's a bit slower than before because we have a lot of pieces. Let's see how the constraints look like. So right off the bat, I can see a lot of the soft constraints got broken quite fast because of that distance threshold that we have. And that will just mean that we're going to get more individual fractures like this. We're not going to get really these pieces, except when we come to here. But here you can see everything is broken already. So if you remember here, we're actually doing that based on distance, right? So if we plug this in, that's going to work in a bit different way. We won't be able to see our constraints because they're literally just points. Well, I guess we can see them. But you can see they're not going to get fractured in this case, where before they were getting fractured, they were tearing apart. And now they're not. They're sticking together more because they're not exceeding that limit, and we get more glued clusters together. Not glued, but not with a glue constraint. Just they're sticking together more based on the soft constraint. So that was giving me a better look in this case. Too bad we cannot see the red glue constraints because they're so tiny. But yeah, that's how that works. If we go back, and I will turn this on for a second. Another thing you can do is here you can break based on impact or force. But yeah, in this case, I was breaking. I did not use it, but you can break your glue based on impact, and then you can say when you break, you can either say you are just broken or you become a soft constraint, right? So there's a few ways that you can play around with that. After we do the main simulation, then you're going to get a lot of pieces, and it's going to look like this. It's going to look pretty tight. I think it looks pretty awesome. And then you do the RBD fracture because we are removing it here just for testing purposes. Actually here, we only get this. Just this part. And this part is actually what we are using for the upres. I'm not uppressing anything else except for this part. So the upres system is everything that's on this side. I'm going to turn this off. And then I remove it here again. And this is actually what goes into the upres. I do the upres here. It's the same thing, just 3 different variations, but it's literally just doing that scatter with the Voronoi fracture like we were doing in the simple example. It's the same, just more of them. So we upres it here, assemble it. It's the same setup as before. I use the interconnected constraints to transfer that attribute, activate it. We go through the same thing and then we cache this. So we get this big constraint network and they're all being activated just like they were in the simple example. Absolutely the same setup. This, I don't think we need this. Am I using this anywhere? Just give me a second. I don't think. Nope. This should not be here. I'm sorry about that. It's probably making some of my setups a bit slower because I was using it like that. Also, I'm not using any of this here. Yeah, like I said, I will clean this up for you after. This is the edge removal, so that's very cool. I'm gonna skim through it, but you guys feel free to play with it. What I do is I take the static geometry, so just the static geometry, not the simmed, because it's not supposed to move, because we're gonna do a transfer here. We're gonna blast everything that's inside, do a facet. It just makes this a bit more stable with a facet. Promote the primitive name to points because we need that name attribute, and because we are gonna remove all the primitives here, we need it on. We need that name on the points. And now this is interesting. We do a fuse, and with a fuse, we're gonna go from 2,600,000 to 500,000 points, and we create a new ID attribute based on the near distance from the first geometry, and then we add them together. So quite a lot of points, because here there are more points. See these, like there's like 3 points here. They're gonna inherit that ID that was just here on probably, well, let's see. It's so difficult to visualize this, but a lot of points got removed. See how a lot of points here are overlapping? They get removed. And now here, there's just 1 point, right? 1 point here. But here, there's like 2 points, or maybe in some cases, even 3 points. These 2 points are gonna get the ID, an ID the same for both those 2 points. And because that ID is the same for those 2 points, it gets a primitive in between. It's super tiny and small, but there's a primitive between those 2 points now, like a line. And if we transform that now, you can see that line forming, because some points are moving and some are not. Some of them are still static. And if we push through, you can see that a lot of it's very cool actually. It's super simple, but it's very cool. The points that are not moving, like here on these edges, these points are not moving yet. But the points right next to it was moving on a different piece. And that will now create a map that we can use to remove everything that's inside. So we measure it, we promote the length, we put a color on it, so you can see everything is dark here. This is black. We transform, we get this attribute now based on the color. We transform the pieces now, so you can see everything is going to be moving, and that attribute is still going to be on the points. So you can see it's very cool. But let me remove tint back faces. Everything here, this is the same piece. but this piece has not detached from itself, therefore it doesn't get any values, but everything else started detaching, right? So everything that has detached, it has an edge because it's broken. So we just have to now remove everything that's, no, it's on this side. Everything that is black, we just have to remove it. I'm not sure where this is. Where are we? CD is on the points, and here it's on the primitives. So we have to just put it on the primitives like that. So now everything that's detached will have an edge, and everything that's not detached will not have an edge. So that's pretty much it. The only other thing that we have to do now is run it through a solver, because sometimes, let's say if the point falls down, the distance gets shorter, that's not going to work. They're actually going to be flickering, going in and out. So we have to run this through a solver, and this becomes a bit slow. Essentially just maxing the color coming from the previous frame and coming from the current frame. What is the max? So it can never go backwards. It can only, once it becomes 1, it will always stay 1 because we're using the max value. And then when you cache that out, you get this, and it's a very solid map. And like before, we remove it, and we have the inside. And here we have the outside. We just remove, we just get all the geometry. We've removed the inverse. So here we have the inside pieces. Here we have the outside. We transform it. We get this. You can see there's nothing inside. And we get, once we combine it, we start getting some of the edges back, but not the edges that are inside here, because if it hasn't detached, it doesn't have any edges, but all the other guys are going to have some edges connected to them. And that will give us quite a solid edge. It's especially better for long shots like this. If you go super close, if you're doing like a macro shot, then maybe you're going to have to finesse this even more. But for this, it was working fine. And we do the same on the left. You guys can check that out on your own. Let's continue with the RBD. So this is the secondary RBD system. This is what gives us a lot of the juice. This is the juice. This really helps quite a lot. You can see how many details we get with this. Actually, I think we're previewing this. So look at that. Look at how many pieces. I reckon we can even have a few of them that are a bit bigger. They're all quite uniform, too uniform, even though I was creating like maybe with a few of them so they're a bit bigger. Let's see. Just some more variation. I guess we could do another attribute randomize on this. You can say piece scale. And we don't want to set it, we want to add values. Let's put this back to 3, small. And then here we can then base it on a custom ramp. And like that. So we would just add more just to some of the pieces. So you can see how that would create more variation. So this actually looks much better than before. So there you go. I made it better. So how does this work? It has a trick. It has a trick in it that if you remember that RBD bullet solver actually has that built in. And that thing is called emit RBDs. So this will continuously emit RBDs that you feed into the system. Because we're doing it manually here, it's not going to work. The way we're spawning these is quite interesting. I'm using the debris from source. Sorry, the debris source. It's what it's called. I don't want to go through the whole thing. It's going to give us a nice map of where to spawn the debris. And it's just using some fancy attributes and the way the distance and the age and lifespan is computed. And so you need all of those attributes here. Well, at least some of them. So again, here we have just our static geometry, and here we have the points, put them on transform pieces. We calculate the debris and you get this map, which is very cool by itself. This could be used for an effect by itself. And then I'm removing everything based on the color. So you can see like so. This is to remove even more. We don't have to. And this is essentially giving us a p-scale attribute, and then orient, angular velocity, and velocity, and changing the name just so that nothing gets confused. I'm sorry that I'm going super fast through this, but it's quite a lot to explain everything. So yes, like I'm saying, it's good for you to just go through it. And if anything is not clear, just let us know in the comments, and we're going to give it our best to answer any questions. Here I'm just grabbing from a few pieces from our main geometry. So you can see it's not super efficient. You can just create it in a different way, blasting them, caching them. So we just have a few variances in the points, putting them in the center like so. So they're all together, assembling them, and then copy pasting them to our debris source. So this won't do, this is essentially what we're going to use for our emission, like so. And this is not super important. Then here we are defining our last name based on the previous name, the frame number, and the point number. This is important. So each frame, our points are going to get a different name based on the dollar frame. And that is important because on each frame, we are actually injecting them into the simulation. And the last time I tried this, it gave me a crash, because this is a lot. Like this is, it becomes quite slow. And I hope it's not overcomplicated to understand. We do need our RBD colliders. So this is our RBD. We do need this because our small pieces need to collide with the big pieces, and there's a separate sim, and we need the ship to collide as well. So we have both. So once we have all of this, okay, we go inside, and this is the trick. Let's see. I know there was something that was redundant here. I think it's this guy. I think I'm bringing in the ship twice because the ship is ship collider and RBD are here already. Okay. I'm going to remove them for now just so we can see what's happening. So what we're doing, we are creating a blank. This is a blank, and we are inheriting velocity from points. A blank RBD object has nothing in it. You see? Nothing. Then we do a SOP solver. Inside the SOP solver, we actually bring in our points, just literally just bringing them from the outside in. We put them in a group called secondary because I'll show you in a second. We can just do this. Merging them. We're merging them together with our nothingness. This is nothing because we're not importing anything. But if you combine it here, it's gonna loop. It's gonna go here, do this, and then come back here, and then it's gonna have something. And then we're injecting on the new frame, we are injecting new pieces again. And the old pieces are just going to be simulated, continue being simulated, but we are injecting new pieces and it just goes round and round. That's why it becomes heavy. So you can see now we are spawning everything like that. There's a lot of pieces that get spawned here, but it's still, for how many pieces we're spawning, this is still quite fast, I think. You can see, like, it's not chugging that hard, and we are spawning millions of pieces. The reason for that group here is because right here we are removing everything that is in that secondary group, essentially everything. If you fall down between 10, just get removed. And if you remove it in the sim itself, or after it drops below 10, it's just easier for the sim. Otherwise, it would continue falling and it would be just unnecessary, because we would have to delete them probably anyway after the sim. Then why not remove them in the sim already? So after you put back your colliders, they're just going to collide with everything. And this is how it looks like. So you can see everything is colliding with the ship. You can see the silhouette of the ship quite clearly, and everything is dying after they reach -10. So it's more efficient. And you can see how much, like, it almost looks like a fluid sim, right? There's so many points that we're spawning here. And then we copy them back to points again, because we were just caching the points. We copy it again, and here we did our scale. So you can see this is quite uniform, but now we have some of them that are a bit bigger, so it makes it more appealing. Woo! God damn, that was quite a lot. That was quite a lot to go through. My hand hurts a bit. But that's the gist of it. That's kind of the overall overview of the RBD. So in the next video, let's go through the snow setups. All right. Right, here we are in the snow section. Let me showcase one of the snow setups. I'm going to be focusing on the global snow. All the other setups are pretty much the same. Oops, why did this one kick in? It's probably an old cache. Oh, I know why. Yeah, there we go. This cache is old. So this is the global smoke. The snow setup, and you can see how it has that patchy kind of snow look, and that was quite cool to get that look. So it's not just a random noise, but it actually, the noise sticks to the points, and you get that patchiness that you would get with snow or more icy snow that gets blown. And this it's this system. So these are all the same setups. That's why I'm only going to focus on one. And the other ones you can explore on yourself. They have a few caveats that you can find. It works with two different systems. And initially I was trying to just do a system where I don't have to use the smoke pyro. I ended up using both in combination with each other, just because it was working a bit better. But I will show you how they complement each other. And it's quite important just after this. All right, so I was using Axiom for this and not your standard pyro, because it's faster. In this case, it was quite fast. And let me show you this. Oh, so yeah, it's actually simming up. So it already simmed all of this because it started at minus 150. So that's how fast it is. So if I continue simming, you can see that Axiom is just killing it in this example. It's super fast. So I put a rule to myself: if this smoke takes more than 2 minutes, I won't use it. So it literally took just a bit under 2 minutes. So I used it. So what's happening here is just simple Axiom setup. I'm using a axiom source as a shape and axiom sink, so it actually dies off at this point, so it's not just doesn't continue. An important thing here is, well, for this one, I guess, where is it? Let me see. So right here, the reason why you would want to use a smoke sim is because you get this velocity. And I'm a bit surprised I didn't use it here. Actually, that's weird. That I just, oh yeah, I know why. Oh, that's fine, because this is actually in front of the ship. All right, never mind. Let me backtrack. So this sim, the same setup, but it has the ship as a collider, so you can see it here. And the ship is moving up super fast, and it's actually colliding with the sim. The reason why you would want to do that is if we do a volume split here, slice. No, what is it? Volume slice. Yeah, volume slice. That's what I was looking for. We get you can see we are getting advection from the ship. The simulation actually kind of curves down, and the velocities are different. So that is kind of the main point why you would want to use this. So you get some interaction, and also you get some cool. You can see what's happening here, the collisions and everything. So that's kind of why you want to use a smoke sim. Plus, so you do this, and then you combine it with a box, a custom wind, which is essentially just a box, VDB from polygons. We are creating a velocity, and this is our wind. What's happening here is we are doing a kernel noise, plus we are without this, we just have we would just have a wind. We don't really need this. We would just have a wind direction that we can control here. So wind direction. So 1, it's going to go up. 1 in Z, it's going to go in Z. So we want it to go in X. And now we just want to multiply it. We want to multiply this. We'll add the direction plus the noise and put it here. And now we have 1 wind strength. I went one step further, and you can create like a little asset out of this where you, yeah, I'm not sure. Wind tunnel. So this wind tunnel, it's going to do the same thing, but it's going to combine. You have dual noise, small noise, big noise, or both noises together. So if you have only the big noise, it's literally just a big noise. Small noise, it's going to be the more, I guess if we push the frequency up. So you have your big noise, which is probably a bit too small. And then the small noise, and then you dual them together. Probably the small one is, the amplitude is too high. So you get a very cool noise map like that. And this you can use as a wind, and it's quite fast and you don't need to sim it. So that's essentially what I'm using here in this box. And I'm just using a rubber toy, pushing some color through it, and then doing a pop network. And this is how it looks like. And this is literally right now just using this box as the wind, and 1 pop advect by volumes. And that's what I'm using. I'm advecting it with volumes, and this is what you get. You can see it's a very, very natural wind effect. happening here. And we're not doing any fancy simulations with Pyro or anything. It's literally just that box, and everything is super fast to sim. And it's looking super organic as wind or rain or anything like that. So that's this setup here. So now the only trick was to make it bigger on a bigger scale and pump in some Pyro as well to get more interactive, just a more interactive wind. So actually I'm going to work on this side because we have the ship here. So let's see the snow. We bring in all of our RBD. I was scaling everything down just because it was easier to work with the numbers that I had. But yeah, I'm adding some color here, blasting it, so scattering, blasting it. So we have a very cool map already, and this is happening on each frame. I cached that. Oh, for some reason I didn't cache it with when I blasted the. Oh well, it doesn't really matter. I'm not using this color anyway, so we can just color it back to white just so it's not confusing. And I bring in my volumes. They're quite big, like so. In here, and they should be, if I look at the scaled down version and my volumes, my sim should be in there. Yeah, it's quite huge. So let me see. Ship animated. So this guy. Yeah, so this should be here. That's why it's so big. Yeah, so see, this is colliding with the ship perfectly here, as you can see around. Let's go down again. So in the sim, there's a few things happening. Not sure why it's complaining here. What do you need? Are you sure? There we go. We have our ship as a collider. It's quite important for it to collide. And I remember I'm only spawning from the RBD in this case, so only this, and it's coming from the broken edges. If you remember that map that we did, that's what I'm spawning from. I'm bringing in my wind, main wind, and the pyro push. So pyro push is the pyro, and then the main wind is the main wind tunnel, which is coming from here. You can see it's quite big, and this is how it looks like. That's the main wind tunnel that's pushing everything. And then the pyro is just adding an additional spice to the advection, essentially. So let me remove the ship so it's faster. Otherwise it does chug just a bit. There we go. So you can see it's quite fast. And there's nothing special happening aside of this part. And what is happening inside of here is actually very interesting. So we're doing a PC find and a array length. And this by itself gives us this color. That's how we are getting the color. So it's literally checking the points on itself and just seeing, it's finding them based on a radius. So the ones that are closer together are going to get like a nice color like this. And the ones that are further away, you can see at the beginning, it's just finding itself here. So that's why it's super white. It's not the best in the beginning, but it gets quite nice here. It gives us a very nice snowy and icy feel already just from this color. So we're using this is based on a radius. So if I disable this animation, you can see if I put this to 1, it's going to find everything. But then once you start getting lower and lower with the radius, it's gonna only be finding the closest points. So 1, 0, 6, you can see everything darker, 5, 3, 2, 1. And then obviously if you go even lower, it's only gonna be finding the clusters kind of that are more together and closer to each other. So I think 0.3 was something that I was working with. Yeah, it's nothing to it. PC find length, length is essentially just a length of an array. So that's going to give us a number of how many arrays is it finding here, and then just putting it through a fit. And with this fit, we are essentially controlling the map a bit further. And with this, I'm also putting it into an attribute. You can call this whatever you want. So this could be a wind. How would you call that? Pocket. And that's wind pocket you can use here. On this side wind. So everything that's white right now is going to get an additional wind that's kind of blowing backwards. So that's why I called it like a pocket wind, because so if we push this quite a lot, you will see that everything that's white will try to go the other direction. And you can see it's already, you can see how it's changing it. Like some points are kind of dragging behind more. And let's go crazy. Let's go 2K. You'll see what's going to happen now. Well, see, it's stopping it quite a lot. These forces are super strong, so it's still pushing it forward, but let's actually do a preview. Might be fun. So everything that's white is gonna be pushed because we are essentially just creating a fancy mask. But then when it becomes, everything that's black is gonna be pushed backwards. Everything that's white is gonna be still pushing forward. So this will create like a very cool pocket right now. Yeah, it's crazy. Could be used for something else though. But it's a good logic on how to create these wind pockets and manipulate particles with different masks, essentially. And so yeah, everything that's here is gonna, you just multiply this force by the wind pocket, and I think it was like 20, just a bit, so it was pushing it. But you can also do this based on the here, right? We can say the same thing. Instead of force, we could just add. Oh yeah, I am doing it. So so wind pocket, do it here. And then the amplitude, just put it to something crazy, just so we can see. So you can see it in the beginning, it's gonna held together, and then it's just gonna become crazy disturbant. Right, and this looks quite cool as well, and you can use this for magic. You know, it doesn't have to be for snow or whatever. You can apply the same principles for magic effects or abstract effects for that matter. All right, so let's put this back to 0 because I wasn't using it. And then everything else is basic, just pop wind, doing a simple air resist. I'm not sure where I was getting that attribute. Oh yeah, I know where I was getting that attribute. I didn't end up using this, which is funny that I just saw this. It's a mistake. It's a mistake on my end because I was actually creating that attribute here. It's called air resist here. And so the air resist is just another map essentially where everything that's white is going to get more air resist. Everything that's black is going to get less air resist. So we need that. We need that map for our wind for this to work properly. So good catch on that one. So now everything it's actually going to go a bit slower. It's a bit slower because the wind is resisting it just a bit. So there you go. And it's based on that map as well. Everything else is quite stock, and then you bring in the ship and you get collision with the ship. When you put all of that together, you get your snow like that. And then you just, I was doing some, probably nothing major here, just some tweaking with the color like that. Transferring, not sure why I transferred it, to be honest. Oh yeah, putting it back into scale, otherwise it's super small. And then putting the basic particle scale, CD scale. This was just to create my own attribute, and this is a point for USD. Color is called something else in USD. And because it's called something else, I kind of had to, I just used my own attribute called CD scale, because based on the scale, I was actually changing the point number later. So I just created my own attribute for that. I was multiplying down the velocity because I was getting way too much motion blur, and that was it. I exported it out. All of these guys are very similar. I'm gonna let you to play with this, so good luck. All right, so that's when it comes to snow. That's the overview. So let's jump into what you have to do to make this workable with USD and Solaris. All right, so jumping from here, let's go backwards. Don't mind this. Like I said, I'll clean this up later. This is the main one. If you go inside, you're going to see all the caches that we had here. And so you bring in your cache. In this case, so this is the outside, and you kind of have to do this. Otherwise, you're going to be entering a world of pain again. Everything on the outside, everything on the inside, separated. You delete the name attribute. You do not need it. It's absolutely essential that you delete the name attribute. Otherwise, it's going to try to bring in each piece as a separate piece, and it's not workable. Trust me. Try it. I dare you to try it. It's not going to work properly. You still have the inside and outside. So, but because we're splitting them, you kind of don't need that group because they're splitted by geometry. If you do want to have that group, you can just put down a name, and you can say name from group. And now you will still have that name, but it's going to be just inside and outside. All right. I hope it should work. I do wonder where I had it. Here we go. It's not working here anymore. But yeah, attribute delete, name from group, and I think you have to say all, right? I think that's what I missed. Yeah, all. And it's gonna use your groups as your name, but we don't have to do it here because we're splitting based on geometry already. And then you can put it, and I deleted the groups because I was like, okay, I don't need the groups, so I removed them. And then you can put it through a USD configure. This is still a bit new to me as well. But essentially what you can do is, see here, it's the UV attribute gets changed as well to called ST. You can untick that and it's gonna leave it to UV. You can also set here, so the topology attributes, you can set them to static. And now it's not gonna transform the UV, or if let's say you have a rest position, it will transform it, but it's not gonna try to update it with each frame. It's only gonna import it once. That's how I understand it. So these are just some optimizations that you can do. See, because it's either animated or static, and then you set default values here. But it's not essential. It's not essential to do this. What is essential is removing the name and then exporting it as a USD attribute. So there's a few caveats to this. So USD export, you put this down, export and frame range. And you can see you can already separate files per frame. If you do want to add $F4, you can separate it per frame, but just like with Alembics, you can just put it in one USD file and do not separate the name. And this will create one file for USD to read, and it's going to be much more optimized. So that you have to do that for all the geometries. So you can see here I was importing everything else inside, outside. So, and then you can kind of combine, you can see what you're getting, right? I didn't need the UV. I thought I'm going to add some displacement on top, but I ended up not using it. All right, so that's the catch that you have to do with the USD. And now if we go here, let's check one setup. We don't need that, just for testing. All right, so what we're bringing in here is with a sub layer, you just say file and you bring, you read in your cache, your USD cache. And this is the outside, I guess. And you can see it's decently fast. It's not super fast, but it's okay. Not sure what that is. Oh yeah. So that's correct. Here, it's gonna start breaking. So these are all the inside pieces, and these are all the outside pieces like that. So we have that, and we have all the inside pieces for this and all the outside pieces for that. So these are our fractures. I'm bringing in my ship, just using a SOP import, all of my glass. Not sure what that is. Oh, the small RBD. Merging everything together. I'm doing two lights, a dome light and just a distant light. And we already have a tutorial that Saber did with rendering, how to render water, that uses these exact same setups, and he goes into much more detail because he's just focused on that one topic. So check that out if you are still unclear. I'm also doing a geometry light here. So I'm actually bringing in all of the points from the windows, right? And on each of them, I'm actually copying a light. So that's quite cool that you can do that here. I'm just transforming them forward a bit so they're not intersecting with the actual glass. And that serves as my light as my geolight essentially for the windows. They're not perfect, but I don't think you actually see the problem in the end. This is the material library. It has a bunch of materials. A lot of them I need to clean them up. They're not being used. You have your, you assign your materials here. And then I'm also importing the camera that I did. And then you just render it, render everything. I'm not sure which one. I think this one was the render for all of this. An important thing to note is if you want motion blur, you have to put down a render geometry setting and put enable motion blur and then velocity blur. So that's important. So this is quite a simple setup. This one is a bit better, not better, just has more tweaks. And this is for the snow. So for the snow, and this is why I like Solaris, is if you just need to render out different passes, you can just copy paste everything here and just put it here and create something else. And all the materials, everything is just gets just duplicates it, and you don't have to worry about it. Then you can create multiple strands and different variations. So that's very cool. So I bring in the same thing, same lights, same everything. I don't assign any materials this time to the ship or this destruction, because I don't have to. It's going to be faster that way. I bring in all of my different variations of snow. As you can see, I did a few variations. One is very close to the ground. One is a bit further. This is the global one. And then this is the one from the ship that we were looking at. They're using the same setups, just different emitters. And I wanted to separate them into different passes. Essentially, I wanted each wind to be a separate render, because I knew that I'm going to tweak them later in comp based on their intensity, when they're spawning and all of that. So what I did was I put down a switch, literally just switching between the different snow layers like that. Oop, please don't crash. Okay. And in the different karma renders, you can go to advanced, and in the scripts compartment, you set it to Python, and you can go to your Python shell. No, not that one. You can go to your Python shell here, and you can say this switch, put it here, dot set, and then set it to 2. And if you press enter, it's going to set it, right? So you could just copy this, copy it. And when you're here, you paste it. And now every time you're going to press this render, or this render, or this render, it's going to change your switch. And that's super efficient, because yeah, you can do it manually. Yeah. But this is cool. You're in the cool town now. You're hanging out. If you use this, you're hanging out with the cool kids. So that's why you want to do this. So yeah, you do this. Like I said, the render settings and everything, that's something that Saber covered extensively in other videos. So please do check them out on how just rendering with Karma. You can find them on our channel, or we're gonna link them here as well. And then the other thing is that you have to do is use a matte. So the way to do that here is you have to, so everything that's not the snow, which is the RBD inside, outside, and the ship, you put them here. And then you put them as a matte. And what that will do, if we look through our camera, it's going to remove the ship from our renders. So let's actually check out number, what is this, the last one, 5? 4? So if you don't do that, you will get a ship here. Not a ship, but the snow is going to be visible to everything. What we want to do is actually just matte everything else out. So later in comp, we could just A/B everything together. So if you don't do this, if you say none, actually, if you say matte, and then let's put it to phantom, you will still see all the particles, but now the snow will get, it will get interaction from the geometry, like from the ship. It will pick up colors, it will go into shadow, like the ship is still going to affect it, but you see we still have all the snow. And if you just press it, you put it to matte, it's going to matte it out. So that's how you put something to phantom, or that's how you put it in matte, if in case you guys were wondering. Okay, I think that's it, guys. I don't, like I said, please do play with this yourself. We're going to be providing the file. It's going to be cleaned up, and It's going to have some more nodes on the side. I think it's a nice playground. It's a very good, robust project for anybody to explore. Please try to recreate it. Try to make it better. All of that. The way we try to encourage learning is by showing you guys the path, showing you guys the necessary steps you need to do. And then we kind of push you a bit in the water for you to swim by yourself. And that's how, I feel like that's the best way to learn. And like I said, if you have any additional questions, let us know. We're going to try to help out. In our workshops, like when I was mentioning the destruction workshop, Saber does go literally from scratch, step by step on how to build really next level destruction. So if you're interested in that, please do check it out. Check out our other tutorials here on YouTube. And actually, before I go, just wanted to quickly show you the composite as well. So give me a second. All right, here we go. We are in Nuke. We're going to be taking a look at the composite now. Now, just a word of caution. My composites can be a bit a bit messy and sometimes a bit all over the place. So maybe some things they're not mathematically correct. I usually just try to look at the image and see how it looks. But yeah, you've been warned. So this is the raw render that we got from directly from Karma, and you can see it looks okay. It's a bit flat. Maybe some areas need some focus, but overall it's quite good. Now I would say that this is a denoised render, and here this is how it looked like with the noise. This is the actual raw render. You can see there's quite a bit of noise, and after I denoised it, most of that was gone. And I was using the denoise on pretty much all the passes, even the snow passes. You can see this is without denoising and this is with denoising. And you can do denoising at render time or after. So after, you would go into the composite network in Houdini, and you just put down an AI denoiser. You plug in your render and you export it again. So that's what you get. All right, so this was the raw render, and here I started doing some corrections. So first, I thought that this area is a bit too bright in comparison to this, so I just lowered everything down here. I did a radial, and then only the distant light got brought down. And if we look at a contact sheet, we can see the passes that I have. So this is beauty pass, this is the depth pass, geolite pass, normals. I believe this was the HDR, and the distant, literally just the sun, the backlight of the sun. So yeah, I wanted that to be a bit darker just to add more focus to the main core of the ship. And then some more corrections on top of that, making this a bit brighter, also adding glow on this. And I wanted to add a bit of that anamorphic Star Wars glow. So this is how the glow looks like. I put it back with a screen, so nothing gets above 1. And pushing back the HDR a bit, because we were losing some details here in this area. But you will see how all of that comes together. Here, for some reason, the alpha got messed up, so I just used the original alpha and I copied it back here. So my alpha is still intact. Some of these corrections are quite small, as you can see here. And so I was making this darker again. So a lot of these are kind of redundant. That's why I was saying it's my kind of workflow is not the best. Sometimes I redo the same operations. So yeah, just so you know. So I added some motion blur here, color corrected. It was looking just a bit too blue, even though, again, color correction would have to go here. But as I was working as an artist, I just did it here. I added CD focus. That is mostly visible here towards the end. Probably too much, but I really like the anamorphic bokeh. So I said, what the heck, I'll just do it. I added some chromatic aberration here on the edges, just so you know how it is. When you're comping CG, you want to make the image look worse. Instead of if this was actually a photograph, you would probably be using probably removing chromatic aberration. So there you go. Color correcting a bit, getting a bit more into those bluish teal tones. On the left, I was adding a matte painting. This one is done by Stephen Corman. So I really like this, and I just wanted to use it as a background. So I projected it on the cards here. Where is it? Here we go. Projected it on the cards. So just a basic projection on a 2D card. And then I exported the camera from Houdini. So the camera is actually moving and it has the camera shake, and then you would just use that and in your scanline render, and that would essentially give you the same camera that I had when I was rendering. And you can see it's moving up, it has the camera shake, so everything is going to be matching correctly. And I did this twice because, so I really liked this frame, but I wanted to have some of the highlights and kind of the God rays passing here. So what I did was I just keyed over that part, and I just put it over. So there you go, like that. I just wanted some of that happening here, and this was working fine for that part. I also added some ZD focus, so it's not completely in focus. And then this would go just behind our scene. And you can see it's matching quite well in terms of color and in terms of contrast. It's looking good. Looking good so far. I did add some additional glow on top. So what I did was I just used only the kind of the brighter bits. I blurred them out, color correct them. I formatted them because, well, in this case, I guess it wouldn't be necessary. And then I put them over. And this would just give me almost like a lens flare coming from the top, and it's quite natural occurring because it's happening only where the bright parts are. And you can see it's going to be moving because at the beginning of the shot, the camera is a bit lower, and we're going to have less of that lens flare. And towards the end, it's going to be more because the camera kind of panned up. You would get some lens highlights that usually occur. If you don't have a matte box over your lens, you will get some lens kind of like flaring in a way happening on the top. Then this part, I was just adding a lookup table. And this was just to add a bit of, I guess, natural teal and orange colors really fast with a lookup table. But it's not super necessary. As you can see, it doesn't do a lot. But what you have to do is convert. In my case, I had to convert everything into sRGB. I applied the lookup table, and then you would convert it back to ACES. So you're back in the same, you're back working in the ACES color space. And keep in mind, I'm always working in OCIO, so I am by default using the ACES color space in Nuke. All right. Here we skipped all the snow. It's a bit slow to run to preview because there's a lot of passes, and I was doing some things to them just to make them flow a bit better. This one, so this is just the one from the ship. Another one just on the ground, just some, you can see just a few of them are kind of lifting from the ground, and they're sticking to the ground fairly well. This is a global one, and then another global one. But what I did for this one is I just defocused it quite a lot and brought it back up. And this actually gives you a feeling that of more global wind. It almost feels like kind of if you would use a pyrosim, almost like smoke, but just like overall, it gives you a feeling that something is passing, like a bigger swifts of wind are passing through the screen. So that was that effect. And you can see for some reason, this becomes very blue here, and I don't know exactly why, because then I color corrected down again. And yeah, that's how it looked. This is how all the passes look like. And this is some more renders. And yeah, this is how the denoise versus the not denoised version looks like. And we are gonna add everything on top like that. So you can see that's how it looks like. Very cool. We did the lookup table, although not super necessary. Here, I actually rendered a depth pass. It's not really a depth pass, it's a volume pass. So this is actually a volume, but the render was, so this is, render was a bit noisy. And I did it in two parts. That's why I have a few frames here and a few here. Don't worry about this. Just I used a different workstation for one and then the other. So the noise was, it wasn't that noisy in other areas, but it was quite noisy in the geolight area. And I couldn't really fix it without getting super long render times. So what I did is I just excluded it, and that was working fine in this case. So I just removed it from the actual render because I decided I don't need it, even though it would be a nice touch to have this geolight. And even when I put it through a denoiser, it was still too noisy. So actually it was just a bit smudgy from the denoising. So all right, so I grade this a bit. I add the, here I was adding the depth pass from the raw render, because I was using, I had to defocus this as well. So you have to defocus this the same way you would defocus this top render. So you just copy paste this one, and then you defocus your render, your depth pass. Otherwise you're towards the end, because I was doing quite extreme defocusing here. If you don't do it, and if your raw render has it, you will see you would get a mismatch like that. So once you do it, it's going to be perfect like that. Cool. So we have this, and this is looking quite cool. And it could work as it is if you had a scene that is super, that has a lot of volume and it's super white, a lot of snow happening. And so this would kind of, it could work as it is, but I did want to add some more color correction to it. And specifically, I had these images as a reference here. And you can see Star Wars can, sometimes they go quite dark. You can see here in the histogram, they're literally kissing the blacks. In some cases, they are maybe going a bit too far, but like this, I really like that, where it's where the blacks are just a bit lifted, like you see here. It gives you that really cool cinematic look overall, almost like if there's a fog or a haze pass on all the time. Like here, there's literally no real black values. As you can see, everything is a bit lifted. Here, there are a few here. So let's say this frame is a good example of the color correction that I wanted to go with, or this one as well. You can see the blacks are kind of just a bit lifted here. If you compare it, well, this one is kind of quite dark, but if you compare it to real black, they're still a bit lifted. So this was the contrast that I wanted. And so I started doing some color grading. So color correction, just bringing everything down. And yeah, I tend to use multiple color corrections and grade nodes. And in this case, I usually would like to name them properly, but in this case I didn't, but just so you know. So this is what that is doing, and I'm adding some glow on top. You can see here we're getting some of that orange glow happening from the lights. I wanted more orange because I felt like it was a bit too monochrome. Not that there's anything wrong with that, because I really like how this was looking after we added the snow. Even this is looking good, and it is quite monochrome, right? We're just in the blue colors here. We do have a bit of orange, and that's mostly coming from the lookup table. If I remove it, we are more in the blue space. So once I added that, I just did a key like that, and everything that is kind of bright is coming from the lights. So everything that is coming from the lights, I just wanted to have it a bit more orange, and you know, not much, just like a touch more of that orange coming through. At some point I was rendering out just the lights solo, so I could just change their hue and their glow, but I didn't end up using that because I was using a keyer. All right, so this is where most of the contrast is coming from in this grade node, and literally just bringing down the gamma. And I'm looking at this 0 bar on the waveform. You can see if I go down, even here, if you go down, nothing really gets completely clipped. It will do like a really nice, how would you say it? It squishes everything quite nicely. So nothing gets completely clipped, but you can see right now we are kind of, it's a bit too dark, right? This is a bit too contrasty. That's why I like to have a reference. So if we do a wipe, and you can see this is kind of the area I want to be in, and this is way too contrasty. So let's start dialing it back to where we want it. And I'm really looking at this area and maybe this area to be the same. So if you can select this area here, I'm looking at the hue, saturation, and value. So the one on the right is B. So value in B is 0.05 at this place, and here we are at 0.06. So we are pretty much dead on when it comes to contrast. And if we look at this area, so B is 0.03 and our area here is 0.03. So pretty much perfect when it comes to contrast on this image. And you can see this was the correction. Even the highlights, so the highlights are going to be freaking, so 41, and the highlights that they have is kind of in the 13. So I would have to kind of clamp down my highlights a bit, but honestly, this looks blown out and this looks blown out as well. And I don't mind having things that are blown out. So it goes back to that, having some imperfections in your image so they don't look as CG. So that's why JJ would be adding lens flares. They would be adding, you can see chromatic aberration happening here. They have quite a lot. You can see here there's some red happening on the edges, and they have, maybe if I find another frame like here, they have chromatic aberration happening on the edges, because that would be something that would occur in a real camera. So yeah, that's what we try to emulate. But even so, let's take a look at this one. Value is 0.19, and we were at 0.08. So yeah, this one is a bit, well, but if you look at this, it's 0.02, 0.02, and everything here is 36. So this area is at 23. This was a bit brighter here. But what you're trying to do really is get a good contrast point and a good get the image in a good spot where, you know, it's still visible. The main points are still visible, but honestly, I don't think everything has to be visible. Yeah, you still want to keep some things away from the viewer. Otherwise, there's too much visual noise. So that's why at the beginning here, if we go back here, all of this looks cool as it is. But this part was a bit, so all of this is a bit distracting. So that's why I would be bringing everything down just so we get more visual information in this part. And this is the brightest part anyway. And this is not that important. We just want to know and see that there's some eyes happening. So it's really a balance of focusing the image, and you can do that with contrast, you can do that with color. So that's why here I was adding a bit of orange. So this area would get more focus and attention because all of this is blue and this is orange. You get a nice teal and orange contrast, even though I wanted to get more into this. I guess this is still teal and orange, but this goes more into that orange greenish contrast and also some teal. So that's what I was doing here, but adding some of that orange and then bringing everything down. So you can see this part still remains, maybe just a bit less contrast like that. This looks cool. Yeah, and then I did another reformat just so nothing is outside of boundaries, and I added a grain, some grain on top, just black and white grain to get a bit of that filmic look. And yeah, that's it. That's the whole comp process. Nothing special, but it's quite. I feel like this whole workflow is quite standard, and it's something standard for me. That's something I do every time that I go through a render, and I do feel like rendering, and well, at least for visual effects and CGI, compositing is very important when you're doing it, just because you always start with you know, something like this. And I'm not saying this looks bad, but you just have to know and think about how you're gonna finish it, so you know ahead of time. Even when you're rendering, you can think ahead that, you know, oh, I'm gonna not fix this in comp, but add this feature in comp. I'm gonna tweak it in comp. It doesn't have to be perfect in the render. We do have an Intro to VFX series here on YouTube, so check that out. I show how to do more rendering, more compositing on a different example that is also kind of Star Wars related. So yeah, check that out.